Okay, so we want to do this next thing. It's called the chain rule. 3.4 chain rule. And here we go. If you have y equaling f of some function, and then u equals some function of x, then you could rewrite this thing, and we could do it first in our Leibniz notation, as the derivative of y with respect to this u value times the derivative of u with respect to x. Right? In other words, in maybe a more familiar way, the derivative with respect to x of f of g of x. How do I figure that out? Well, you're going to first take the derivative of the kind of outer shell part, so f prime of g of x, and then tack on the derivative of the inner part, g prime of x. Okay, so let's take a look maybe at just a simple example before we get too carried away. This is problem 10 in the book. I have f of t, or maybe f of x equals 9x plus 2 to the 3 halves. Okay. This is like number 10, it's not the same. Okay, so how do I deal with this? Well, you kind of envision it as something like a function of another function. So you have u of 9x plus 2, and then you're going to then look at the outer part, which is the f of x, or y, if you'd rather. Y is equal to u to the 3 halves. So you have to kind of think of it in terms of parts. You have an inner part and an outer part. My physics teacher, the guy I took physics with, Gerald Walker, always called the inner part the guts. Okay, there's a good way to think of it. It's just you take the derivative of f of x and then times the derivative of the guts. Okay, so f prime of x, the derivative of the outer shell part, you bring down the 3 halves, and then you have 9x plus 2, subtract the old exponent by 1, so 3 halves minus 2 halves is 1 half, and then you multiply by the derivative of its guts. So the derivative of the guts, the derivative of 9x is 9, and the derivative of 2 is 0, so it's just times 9. And then we can clean it up a bit. So 3 halves times 9 is 27 halves, and then times the square root of 9x plus 2. So that's kind of the idea. We could take a look at the proof. I don't know how illuminating that will be, but if we want to know the derivative with respect to x of f of g of c, and we'll use the second version of the limit form of the derivative, so we want to know in particular the limit as x goes to c of f of g of x minus f of g of c all over x minus c. Okay. And then we're going to multiply top and bottom by g of x minus g of c. Okay. And we'll see we have the limit as x goes to c of f of g of x minus f of g of c all over x minus c times g of x minus g of c all over g of x minus g of c. And then we could do some fancy footwork here and rewrite this as the limit as x goes to c of f of g of x minus f of g of c all over g of x minus g of c times g of x minus g of c all over x minus c. And then you see, well, this portion and this portion are limit definitions of the derivative of, in particular, first f prime of g of c, and then the derivative here. This is the limit definition for the derivative of g evaluated at c. Okay, so that hopefully convinces you that the derivative of a composition like this is just equal to the derivative of the outer shell times the derivative of its guts. Okay, so we want to kind of scaffold you into these problems, and first we start with just identifying the bits and pieces. The book will call this probably decomposition. Okay. And so you are tasked with identifying basically the guts. Okay, so they'll give you some function, f of g of x. In this case, it's 5x minus 8 to the fourth. Right? And it's pretty simple. The inner part here, and I'm just going to call it u, is 5x minus 8. And then the f of u is, let's call that y. That's just u to the fourth. Right? So you're decomposing it into pieces. And then ultimately its derivative will just be this, the derivative of this times the derivative of this. Okay, the derivative of the outer part times the derivative of the guts. Let's look at another. This is problem 2. So you get y is 1 all over the square root of x plus 1. Okay. Rewrite it. So it's really x plus 1 to the negative 1/2. And then I think it's clear. The gut part, the inner part inside the parentheses basically, is x plus 1. And then the outer part y is just u to that negative 1/2 power. Some reason, problem 3, this one always kind of throws people for a loop. Y equals cosecant cubed x. And what are the guts? It's not clear the way they write this, right? So you could rewrite it as cosecant x cubed. And then the guts, well, hey, that's just the stuff inside the parentheses. It's cosecant x. And then the outer shell part is u cubed. And one more, and then we'll start attacking these. Y equals tan of pi x squared. So this time the stuff in the parentheses, the u, is the pi x squared, and then the y is just tan of u. Okay. Okay. So once you can set it up like that, it's pretty easy. You're just taking you can think of it as just going across like this. You take the derivative of this times the derivative of this. It's the derivative of the outer part times the derivative of the guts. Okay. Okay. So let's try it. This is now, I don't know what section that says. Section 2 maybe, no, section 3. Applying the chain rule. Need more paper. Okay, so applying the chain rule. Let's take number 5. So we have y equals e to the negative 2x. And you don't see parentheses here, but you can think of it as e of negative 2x if you wanted to. So the guts part is the negative 2x. Okay, so the u is negative 2x, and then the y is e to the u. Okay. So to find the derivative, what you're doing is just taking the derivative of these parts. Right? So y prime is the derivative of the outer part, which we know the derivative of e to the u is just e to the u, times the derivative of the guts. So the derivative of negative 2x is negative 2. Okay. We have to put this back in terms of x, of course, so back substitute the negative 2x. You get e to the negative 2x times negative 2, and then clean it up a bit. So it would be negative 2 e to the negative 2x. Finally, number 10 that we saw that I showed you before. let's actually do it. The correct version. F of t is 9t plus 2 to the 2/3. So if you need to, and it's not necessary, identify the guts. If you already kind of got a handle on how it works, just do it the way you do it. The outer part is u to the 2/3. Okay, so for the derivative, you just take the derivative of the parts, this times this. So the derivative of this is 2/3. U to the 2/3 minus 3/3 is negative 1/3. And then times the derivative of this. Derivative of 9, t is 9. Derivative of 2 is 0. Then we can clean it up. So 9 times 2 is 18, all over 3. And then I have u, which is 9t plus 2 to the negative 1/3. 18/3 is 6. And then if we drop this down into the denominator, we'll have the cube root of 9t plus 2. Okay, let's look at 16. So here we have f of x is the cube root of 12x minus 5. As usual, I want to rewrite it with a nice exponent so I can apply the power rule. So the guts, that's the stuff here in parentheses, the 12x minus 5. The outer shell, y is u to the 1/3. So f prime of x is derivative of this, bring on the 1/3. U to the 1/3 minus 3/3 is negative 2/3 times the derivative of this, which is just 12. So this will be, 1/3 times 12 is 4. And then drop this into the denominator. We have u to the negative 2/3, or u to the positive 2/3. I still need the back sub. So it's 4 all over 12x minus 5 to the 2/3. And we just have a ton of examples to look like that. We want to sort of make sure we don't leave any stones unturned. Let's look at number 13, maybe. It's basically just doing homework at this point. Y is the cube root of 6x squared plus 1. Right, so I'm going to rewrite it as 6x squared plus 1 to the 1/3. And then this stuff is the guts part, right? So let's just cut to the chase, right? Let's see if we can do this. I'm going to bring down the 1/3 and then times what would have been u, but we have 6x squared plus 1, and then subtract 1/3 by 1. So 1/3 minus 3/3 is negative 2/3. And then I have to tack on the derivative of the guts. Right? So the derivative of this stuff, the derivative of 6x squared is 12x. The derivative of 1 is 0. And it looks like I got it. So simplify, 12 times 1/3 is 4. And then we have an x. And then I'll drop this stuff to the denominator. And I get 6x squared plus 1 to the positive 2/3. Let's look at 19. So I have f of t equals 1 all over t minus 3 to the 2. Right, but you could rewrite this as t minus 3 to the negative 2. Then the derivative, bring down the, you're doing a power, so negative 2 times t minus 3, the guts, and then subtract 1 from the old exponent, negative 3, times the derivative of the guts. And this time the derivative is just 1. So you don't really have to multiply by anything if you wanted to, but it's just to be, there it is. Okay, so it'd be negative 2 all over t minus 3 cubed at the end of the day. Now we're going to start getting a little bit more complicated, throwing in quotient rules and product rules on top of everything, seeing how much you can juggle at once. And so here's 24. I have f of x equals x times 2x minus 5 cubed. Okay, so I got to do a product rule. So f prime of x, leave x alone and take the derivative of this other part. So the derivative of that. So I bring down the 3 times 2x minus 5 raised to the 3 minus 1 power is 2, and then times the derivative of its guts, which is just 2, plus take the derivative of x, which is 1, times leave this guy alone. So it would be 2x minus 5 cubed. Clean it up. So I get 6x times 2x minus 5 squared plus 2x minus 5 cubed. And if you want to get clever, you can factor out a common binomial here. You can actually factor out 2x minus 5 squared, and that leaves you with 6x plus 2x minus 5. One factor of 2x minus 5. And then here, the associative law, I can drop those parentheses. I believe that's because of the associative law. And you get 6x plus 2x minus 5. So 6 plus 2x is 8x minus 5. And you get a nice little answer. Okay. So so that was one chain rule and product rule. Let's look at one with chain rule plus quotient rule. This is 27. Y equals x all over the square root of x squared plus 1. Okay. So I probably want to rewrite it with fraction exponents. X squared plus 1 to the 1/2. That'll make my life easier. Quotient rule, y prime. Low d high, so x squared plus 1 to the 1/2 times the derivative of x is just 1, minus high times the derivative of the low. Okay? So for the low, I'm doing a power rule first. 1/2 times x squared plus 1 to the 1/2 minus 1. So 1/2 minus 2/2 is minus 1/2. Times the derivative of the guts. Derivative of x squared is 2x. Derivative of 1 is 0. And that's all over the low squared. So x squared plus 1 to the 1/2 squared. Okay, we can rewrite this jazzmatazz as what? Well, this part, x squared plus 1 to the 1/2, that's good enough, minus all of this stuff multiplied together. So I have 2x times x times 1/2, that'll be x squared. And you could pull this into the denominator if you wished. It would be x squared plus 1 to the 1/2. And that's all over this thing squared, but that'll just give you x squared plus 1 when you multiply out the exponents. 1/2 times 2 is 1, so x squared plus 1 and parentheses to the 1 is just x squared plus 1. Okay, we ended up with some complex fractions, and to deal with those, we're just going to multiply top and bottom by the denominator here that's giving us trouble. So if you multiply top and bottom by x squared plus 1 to the 1/2, things will clear up for you. Right? So this times this, you add the exponents, you'll get x squared plus 1 to the 1, which is just x squared plus 1, minus this times this. Well, this will cancel with this denominator, just leaving you with x squared. And then this times this, you are adding exponents because you really have a like base scenario. Remember, when you have like bases, a times a to the x times a to the y. You add the exponents, so that'd be a to the x plus y. So downstairs I have x squared plus 1 to the 1 plus 1 halves. 2 halves plus 1 halves is 3 halves. X squared minus x squared is just 0, so it's 1 all over x squared plus 1 to the 3 halves. Okay. Let's look at 49. So here we have g of x. So we have some trig derivatives to deal with this time. 5 tan of 3x. Again, if you want to identify the bits and pieces, you can do that route. So the guts will be 3x, and then the outer shell, 5 tan u. So taking the derivative, g prime of x, the derivative of 5 tan u is 5 times the derivative of tan, which is secant squared, u, and then times the derivative of u, which is just 3. 5 times 3 is 15, and then we have secant squared of u, and u is 3x. 59. We have g of x equaling tan squared of 5x. We could rewrite this as tan of 5x squared. Right? And so the inner part, there's really 3 parts, right? The inner parentheses is the 5x, so we call that u. And then the next step up, we call that z, is tan of u. And the ultimate step, the highest step, is z squared. And so you can get one where there's multiply nested functions. Okay? And in these cases, it's probably better just to write them all out and do it this way. It's a little easier to keep track, in my opinion. So anyways, g prime of x will be the derivative of z squared is 2z. The derivative of tan u is secant squared u. And then the derivative of 5x is just 5. Back substituting, I get 2 tan u times secant squared of u times 5. 5 times 2 is 10, so I have tan, back substitute for u, that's 5x, and then secant squared of u, and u is 5x. Okay, so they can get pretty nasty. Oops, ran off the page there. Anyways, we gave you the derivative of the exponential function earlier. We also want the derivative of its inverse. And I think we can get there using well, I guess we can't get there quite just yet. But ultimately, what we want to do is kind of think of this composition of, let's say f of x is ln of x, no, e to the x, and then g of x is ln x. Okay. So if you compose these two functions, f of g of x, what is that? Well, that's plug ln of x into the exponent e to the ln of x, and then e to the ln of x is just plain old x. When you compose two inverses, you get out you get out whatever you put in. You get out x. Okay? They call that the identity function. Whenever you get out what you put in. Okay. From here, we can take the derivative of this thing using the chain rule and kind of figure out then the derivative of the natural log. So the derivative of this part is f prime of g of x times the derivative of its guts. In other words, times the derivative of g of x. on the right-hand side, the derivative of x is just 1. Okay, so it's kind of like the idea is I'm taking the derivative on both sides of an equation. It turns out you can do that. So here, g prime of x is kind of what I'm after. I know the derivative of f of x, right? So f of x prime, f prime of x, the derivative of e to the x is just e to the x. What I'm after is the derivative of ln of x. I don't know that yet. So anyways, let's keep going. I could divide both sides by this expression so long as it's not 0. So I'll have g prime of x equals 1 all over f prime of g of x. So what the heck is f prime of g of x? Well, I know f prime is e to the x, and then g of x is ln of x. So it's e to the ln of x. E to the ln of x is just x, so it's actually 1 all over x. The derivative of the natural log is 1 over x. Okay, so we have these definitions then. The derivative with respect to x of the ln of x is equal to 1 over x. And of course, x is greater than 0. Okay. The derivative, the domain of the natural log is this. Okay. Then in general, they're going to start giving you formulas that kind of work with the chain rule from this point on. If you have the ln of some function of x, that's going to be equal to 1 all over u times the derivative of the guts, right? Times the derivative of u with respect to x. And sometimes they'll also write it as 1 over u times u prime. Okay, so let's take a look at 1 or 2 of these. We have 75 here. We have y equaling the ln of e to the x squared. Okay, so we can take it into pieces, right? We could say the innermost part is x squared, and then moving up one level, we get z is e to the u, and then moving up another level, y is the ln of z. And then taking the derivative across the board, we get y prime is 1 over z times the derivative of z is e to the u times the derivative of u is 2x, which will equal 1 all over e to the u times e to the u times 2x. So these guys seem to cancel out, and we're just left with 2x. If we had simplified this thing first, I think it would have been a lot easier, right? If we had just taken this guy and wrote y equals, well, power rule says you can bring this exponent down in front of the natural log. So you get x squared ln of e. Ln of e is just 1, so this is just x squared. And then the derivative is 2x. Okay, so sometimes there's quick ways to go through this. Just one example, one more example here, which kind of pops up later. Y equaling the ln of some absolute value of x. Y equals ln of just x, we'll say. So note then we can always rewrite the absolute value as a piecewise function, right? So y in this case will equal ln of negative x if x is less than 0, and then ln of positive x if x is greater than 0. The derivative, to take the derivative of a piecewise function, you could literally just take derivative of the pieces. Okay, so this first piece, 1 all over the guts, times the derivative of the guts. The derivative of negative x is negative 1. And then the derivative of this guy is 1 all over the guts times the derivative of x is just 1, so we don't worry about that. Clean it up a little bit, and it seems that the absolute value doesn't really make it too much of a difference. So y prime is 1 over x if x is less than 0, and then 1 over x if x is greater than 0. Right? So if you're given an absolute value, you can kind of disregard it. You can kind of just say, well, its derivative is what it would be if the absolute value wasn't there in the first place. And that turns out to be kind of true. You may have domain kind of issues to worry about, but we don't worry about those too much here. So for example, the ln of the absolute value of, let's say, secant. Okay, so what's the derivative of this thing? Well, y prime is 1 all over, just pretend the absolute values aren't there. It's 1 all over secant x times the derivative of secant is tangent x secant x. And then the secants divide out, and you're just left with tan x. Okay? So the derivative of ln absolute value secant is tan. Okay, so that's pretty neat. Bases other than E, I talked a little bit about this earlier. Bases not E. The derivative of any kind of exponential expression with a base, the derivative of something like b to the x is always kind of equal to itself, okay, times a constant. So it'll be equal to some constant times b to the x. What is that constant then? So for e, the constant was just 1. So the derivative with respect to x of e to the x, that constant just turns out to be 1. So we get e to the x. For other bases, it'll be an ln of the base. Okay, so k will actually equal the ln of b. I mean, that's the case here as well. K equals the ln of e, but the ln of e is just 1. So you don't kind of see it here. It's just 1 times this thing. So can I prove it to you? Well, you can take any of these guys and turn it into one of these guys and then just apply the chain rule. Okay, so the derivative of b to the x is, I don't know if this is a proof or not, but it's kind of, hopefully an explanation. The derivative with respect to x of e to the ln of b to the x. And then this will equal the derivative with respect to x of e to the x ln b. And then it's a chain rule issue, right? So the derivative of this thing is just e to the x ln b times the derivative of the guts. And this thing up here, x times ln of b, is just like 5x or something. You just get back the constant. So I would just get back ln of b. And then e to the x ln of b, I can rewrite back as b to the x. Okay, so this will, if you want to go the long way, it's e to the ln b to the x by the power rule. So I sort of send him back home, ln of b. And then e to the ln of b to the x is b to the x. And then times ln of b. Okay. Right. On top of that, then, we want to know the derivative of logs with base b. So the derivative with respect to x of log base b of x, then you can just sort of, instead of multiplying by ln of b, you're going to be dividing by it. Okay. So in this case, it'll turn out to be 1 all over x ln, 1 over x times 1 all over ln of b. Okay. So again, why is that? And you can envision it by doing a change of base formula. So remember, log base b of x is the same as the ln of x all over the ln of b. And of course, then you could consider the ln of b, 1 over ln of b as a constant, and pull that out of your derivative. So if you remember, from trig, there are pre-calc, there's a change of base formula that would allow you to figure out like the log base 3 of 5. If you go to your calculator, you would need log base 3 of 5 would be equal to log of 5, ln of 5 all over ln of 3. So that's the formula I'm using to convert this into this. And then I'm factoring out the constant multiple rule for derivatives, and then I have 1 all over ln of b times the derivative of ln of x, 1 over x, okay, which is just this guy here. Alrighty then, we'll leave it at that, and thanks for watching.